Good morning, chemists. It's our last day. It's review day, so I get to sit. So I like that. So as you see, I collected data from you all, and I asked you earlier in a couple recitations, what do you think of when I say the word chemistry? And so I collected all that data and put a fun little word cloud together to represent your responses of what you think of when you think of chemistry. So I do this every year with all my classes, and they basically always look the same. You know, chemicals, atoms, reactions, all those things. There's a new one here I liked. Organic chem better have less math because all my homies hate math in chemistry. I like that one. So I kept generating it until that one would show up because I like that one. That one is a new one. And I did say one word. So they followed the directions, whoever that person was. So, you know, I'm happy to see a lot of people think of acids because we talked about K for a real long time in this class. And, you know, the bad connotation words, difficult, hard, crying, stress, I see those words every year too. And, you know, I keep them up here because that's okay. You know, as scientists in college classes, you should be challenged, all right? And overcoming those challenges is what makes you stronger in the end. And so I want to, you know, speak to that and show that it's absolutely okay to struggle in these classes, but as long as you grow from it, you can take a lot out of these really difficult classes that you'll take in college. And so here it is. I will post it on our Carmen page in the last announcement I make, so I will have it there for you to look and inspire yourself in the future, probably today or later this week. All right, so plan is to do review today, and then we'll blow some stuff up at the end. On Wednesday it was 12:20, but because now we're finally done with 12:20, I figured we would blow up big K. That's what it says up here. So we can just be done with equilibrium. The demo lady, Angie, she's like, I don't get it. And I'm like, you wouldn't, it's an inside joke, big K. Let's be done with big K. A lot of people said big K too, so on this thing. All right, so there's your word cloud. I'll leave it with you. All right, so I am working through the final exam review packet thing, the Zoom packet. All right, it's like a super long document, so I doubt that we'll get through it this afternoon. So we'll just work on it today and this afternoon. So plan is, you know, lecture, we'll just do this review packet, we'll break for lunch, and we'll come back at 2 p.m. and do more review. So what chapter do you want to start on? Do you want to do new stuff or old stuff? Old stuff? New stuff. Yeah, let's do a little bit of electrochem while it's still fresh in our minds because you haven't been assessed on it yet. And then we'll do some old stuff. All right, so let's do electrochemistry. What do you need to memorize there? N-ox red cat, basically. That oxidation, your oxidation numbers increase. Reduction, your oxidation numbers decrease. Right? So let's look at this redox reaction and determine all this stuff. Determine the oxidation number of all the atoms, what's being oxidized, reduced, what's the oxidizing agent, blah, blah, blah. All right, so here's our redox reaction. It's not balanced. So let's go ahead and get those oxidation numbers for everything because that's what's going to allow us to figure out what is oxidized and what's reduced. So what are the tricks for oxidation numbers? It's basically like charge, right? And so the tricks are if you have hydrogen in a compound, it's most likely H+. So H+ has an oxidation number of +1. If you have oxygen in a compound, it's most likely O2-. So that's a -2. And so together with those things, when you have polyatomic ions, that helps you figure out what is the oxidation number of the missing piece. So the idea here, there's 4 oxygens. Each of those oxygens are a -2. So that's a total of a -8. But oxidation numbers have to equal charge. You're sitting up there now. So manganese here has to be a +7. All right, yes. Chloride has what oxidation number? That one's easy. -1. Again, if you just think charge, you're going to be fine. What about the chlorine on the product side? That one is 0, yeah, because this is an element in its like neutral form, right? Manganese 2+ is +2. There we go. All right, so now we track how the elements are changing. And so we see manganese is going from +7 to +2. So manganese is being reduced. All right, the manganese in permanganate is being reduced, while chloride is being oxidized. All right, and that's how we get our half reactions. So that would also make permanganate, since permanganate's being reduced, this is also our oxidizing agent. It's doing the oxidizing to chloride. And then the thing that is oxidized is the reducing agent. All right, reducing agent. So those are all the words that, conceptual words, applying it to the steps of identifying what's oxidized and reduced. All right, so I think the next step is to balance the whole equation and determine how many electrons are being transferred. Do you guys want to learn a trick? Okay. So since we have the oxidation numbers, tell me, how many electrons is manganese gaining? 5 electrons. Okay. So that means the half reaction in manganese, when you balance it, when you do all the steps, there's going to be 5 electrons in that balanced half reaction. So tell me, how many electrons is chloride losing total? One, not real, sort of. So it's 1 chloride, but there's two chlorine atoms in diatomic chlorine. So technically there should be 2 chlorides there, so there's actually 2 electrons involved here. Yeah, that's a small detail, okay? So just based upon those numbers, what's the minimum number of electrons that need to be transferred in this event to make it happen? 10. Yeah, so I think n is 10. All right, this is a small little trick to get that answer, but let's go through the full, balance it and see if we get 10 at the end, and hopefully we do. I don't know. What does my key say? Yes, it is 10. Okay, good. All right, so let's actually balance the whole reaction, all right? So I split it up into the oxidizing reaction and then the reduction reaction. Okay, we split up those half reactions. So I'm going to take chloride, goes to chlorine gas. We balance the atoms first. So this is where we put the 2 in front of chloride. So then the atoms balance. Next, we balance oxygens using water, then hydrogens using H+, but there are none, so we're good. And then we balance electrons charge. So where am I going to put electrons, and how many? 2 on the product side, yes. Is that what we predicted up here? Yes, it was. Okay. And of course, this cheat way, if you, this is a good method to get n if you just need to figure out quickly what n is for the Nernst equation, or delta G equals -NFE, something like that. But if we need to balance the full reaction, then we can't really do this cheat. It's just an easy way to get n without actually fully balancing everything. All right, so that's balanced. Now let's do the reduction reaction. This one's a little bit more complicated. So permanganate goes to manganese 2+. So the manganeses are balanced. I'm going to add 4 waters to balance those oxygens. And then lastly, I add 8 H pluses to balance the 8 hydrogens from water. Now we balance charge. This is where you would mess up, right? So I always like to take inventory of the total charge on both sides. So the reactant side of this half reaction has a total +7, and then the product side is +2. So I need to just make those charges match. So the easiest way is to add 5 electrons to the reactant side. 5 electrons. Because that will bring that +7 down to +2. So it's +2, +2 on both sides. All right. So, yeah, so there we go. Those are our two balanced half reactions. Now to actually make our full balanced redox reaction, we need to multiply both reactions by some value so the number of electrons transfer equally. So I'm going to multiply the oxidation half reaction by 5 and then the reduction by 2. And when we do that, we get new coefficients. So there's actually 10 chlorides, 5 chlorines, 10 electrons. 10 electrons, 16 H pluses. No, that's not right. Yeah, 16 H pluses. 16 H pluses, 2 permanganates, 2 manganeses, and 8 waters. So those are my new coefficients with, distributing those multipliers. And now we can add it up because we see that the number of electrons produced at the anode funnel into the cathode. So 10 electrons, 10 electrons. Is that what we guessed up here using our cheat way? Yes, it is. Yes, it is. So that quick way you can do it just helps you save time without actually fully balancing things. All right, and then we add it up. So 10 chlorides, 16 H pluses, 2 permanganates, gives us 5 chlorines, 2 manganese, 2 pluses, and 8 waters. There we go. So that's my full balanced redox reaction. All right. And so the very, very last question here asks, okay, what is the cell potential for this? And so I give you table values. And so we actually have the redox reactions, the half reactions here. So we just need to figure out where are the matching half reactions on this table. So I see on this table, this is my reaction that's happening at the anode, but it's reversed because all of these are in the reduction form. There's a couple of permanganate ones, so you just need to make sure you pick the right one. So this is the reaction that's happening at my cathode. So this is my reduction reaction. Here's my oxidation reaction at my anode. This is at my cathode. And so to get the overall cell potential, we just do the reduction potential at your cathode minus the reduction potential at your anode. So we keep those table values as is. We just do subtraction with your anode. You can think of it as that subtraction sign is what does the flipping for you, right? Because recognize all of these are reduction reactions, but this reaction is flipped in relation to how we balance that oxidation reaction. So if you flip a half reaction, you change the sign of the reduction potential. So you can think of it as that negative sign does the flipping for you, all right? So just cathode minus anode, but both of those values are in the reduction form. And so, yeah, we just subtract those two numbers. So it would be our E cell, and it's E naught because we are using table values, is positive 1.51 minus 1.36, and so it is something. 0.15 volts is our cell potential. So if we put these things together, these two half reactions together at standard conditions, does the reaction proceed spontaneously? Yes. Very good. Very good. All right, so that's it. All right, so there's that one. Okay, so let's use the same table, and this is more of a conceptual question. Do you understand, spontaneous cells using reduction potential tables? Okay, so given these, given the table, determine if the following reactions are spontaneous at standard conditions. So what is this essentially asking? Yeah, E cell, but what kind of E cell are we looking for? Positive one, right? So if we look at the full reaction, identify the half reactions, if we calculate E cell for these, and we get a positive E cell, then that means this reaction's spontaneous, All right, so let's look at this first one. So the hard part here is like these are basically balanced for you. I didn't give you the half reaction. So we need to ourselves figure out what is the cathode, what is the anode, because that's what we need to calculate E cell. So we need to do cathode minus anode. We need to figure out what is my cathode, what is my anode, given this information. All right, so this first one, zinc and silver reacting. So zinc is what, the cathode or the anode? Cathode, yes, it is the cathode. And then silver is our anode. So we need to find those two substances in our table. All right, and calculate E cell. So E cell here is going to be cathode minus anode. So it is, where is it? Okay, so there's silver, there's zinc. So negative 0.76 minus 0.8. So is this reaction spontaneous? No, it's not, because we get a negative number. Cool. So this one is not spontaneous. All right, what about B? What's special about B in comparison to A? It's the reverse reaction, so just use your intuition. If A was not spontaneous, B is probably spontaneous, but let's check for ourselves. So in this example, silver is now what? It's no longer the anode, it's actually the cathode because its oxidation number is going down. It's going from +1 to 0, while zinc is the anode. So see how we just swapped the identity of the cathode and anode. So when we calculate E cell, we're doing, what are we doing? Silver minus zinc. So it's silver is positive 0.8 minus zinc's, which is negative 0.76. And we do in fact see that, oh yeah, that is definitely a positive number. So yes, this reaction B is spontaneous. The reverse reaction of A, which was not spontaneous. Okay, so now the next ones are a little bit harder because it requires reading comprehension. All right, so in the previous ones I gave you, you laugh. Is that a hard thing to do, reading comprehension? Yes, I know. So that's why we practice, all right? So the first one's a little bit easier because you just go through the steps, right? Like, okay, yeah, get the oxidation numbers, what goes up, what goes down, that's reduced, that's oxidized. These ones are harder, okay? H plus oxidizing silver solid. So we need to figure out what is my cathode, what is my anode, all right? So if silver plus is being, think about this. We have silver solid. Silver solid can really only ever become silver plus, right? Because it's being oxidized, its oxidation number is going up. So therefore, silver is our what now? Cathode or anode? Anode, yeah. So that also means what does H plus have to be? Our cathode. Also think about it this way, H plus in, what does H plus become in a redox reaction usually? H2 neutral, right? So its oxidation number is going from +1 to 0. So it's being reduced. So these ones are a little bit harder because I'm not telling you what the products are, and it's harder to track oxidation numbers. But that's how we do it, right? And now it's the same thing. We calculate E cell with the appropriate thing. So H plus is our cathode. What is the reduction potential of that? 0, yay, okay. I give it to you though, all right. And then silver is 0.8. All right, so this is in fact a negative value, so is it spontaneous? Nope, it is not. Let's think about that. Silver, like silver jewelry. Do we want acid to spontaneously eat away at solid silver? No, then it wouldn't be a precious metal anymore, right? So it makes sense that this reaction is not spontaneous because we don't see silver dissolving away over time, all right? But is the reverse reaction spontaneous? Yes, it would be. It would be spontaneous. All right, let's do another one. Nickel solid reducing zinc plus. Reading comprehension. What is My cathode. Zinc. Yes, zinc is at my cathode. What is at my anode then? Nickel. Yep. Here's another way to think about it, because these are just like metals and they're going from like neutral metals to metal 2+. Zinc as a zinc 2+ after this redox reaction is going to become zinc 0. So it's being reduced. Its oxidation number is going down. Nickel, on the other hand, is going to become nickel 2+. Its oxidation number is going up. It's being oxidized. Great. All right, so then we just do the same exact thing. Calculate E cell, cathode minus anode. So nickel, zinc minus nickel. So negative 0.76. Yeah, zinc minus nickel, negative 0.28. So this is also a negative value. So this is also not spontaneous. Good. Okay. Yeah, B and C or C and D are a little bit harder. You gotta read between the lines. Is that what my key says? Yes. Okay, good. All right. All right, so given this same table, what substance is the best oxidizing agent? What does an oxidizing agent do? It gets reduced, yes. So this question is asking, what thing is the best thing at being reduced? You're going to look for the most positive number? Yeah, so the most positive number. So what is the thing that's best at being reduced? It's going to be permanganate. All right, so MnO4- is the best oxidizing agent because it has the most positive reduction potential. All right, and so since these are reduction half reactions, that's what manganese is doing. It's acting as an oxidizing agent when it is being reduced. All right, now this one's a little trickier. What is the best reducing agent? It's what? Yes, it's zinc solid. But there's two things here, right? So if we can follow the trend, we should recognize that a reducing agent is something that is oxidized. All right? So we are actually going to look for the most negative reduction potential. So that is this, the other side. It's the zinc side, right? But the answer is it's not zinc 2+. The answer is actually zinc solid is the best oxidizing agent, because these table half reactions are all written in what form? Reduction. But since we're looking at the best reducing agent, the best thing that is oxidized, we have to reverse the reaction. So zinc is what's being oxidized. Zinc 2+ is what's being reduced. So we need to make sure we're pointing at the right thing, and so it's zinc solid is the best oxidizing agent, because it's basically, because zinc 2+ is the crummiest thing at getting reduced. All right, so we got to think about that in terms of, our reduction and oxidation half reactions. They're opposite of one another. All right. Okay. Good? Okay. All right. All right, we'll just finish chapter 20 stuff. Okay, so here's another one. Here's our cell. What is our cell potential at standard conditions? So what does that mean? Can I use table values? Yes, I can, because it's at standard conditions. So the hardest part is just figuring out what's the cathode, what's the anode. So nickel is the, what is it? It's the cathode. Yeah, nickel's the cathode. And then lead is the anode. Okay, am I right? Yeah. Okay. And so all I'm doing is tracking oxidation numbers. Lead is going up in oxidation number, nickel's going down. So then we just do the correct subtraction. E cell is nickel minus lead, so negative 0.28 minus what's lead? Negative 0.13. And so we see the cell potential at standard conditions is negative 0.15 volts. So is this reaction spontaneous at standard conditions? No, it's not. Okay. Because because your cell potential is negative. So if we put these things together at standard conditions, nothing should happen. All right, what is delta G? But note here it says delta G not. So am I allowed to use table values? Yes. So the equation we're going to use here is actually negative NFE cell that we actually just calculated. But we can use our, chapter 19 intuition. This reaction is not spontaneous. So what should the sign of delta G be? It should be positive, and that's what we do get. So we just need to plug in those values here. So what is N for this reaction? 2. Yeah, so you can balance the half reactions, but also just recognize, nickel is gaining 2 electrons, and then lead is losing 2 electrons, so that's why N is 2. Right? Faraday's constant, I do give you that on the supplemental information, so 96485, I think, coulombs per mole of electrons, and this is 2 moles of electrons, times E cell, so negative 0.15 volts. All right, and so then we do get a joule out here. I forget what the unit of a coulomb is. I'm pretty sure it's a joule per volt or something like that, and so we do get a joule value out. And so you do see, in fact, delta G is a positive number. What is this? It is positive 28.9 times 10 to the 3 joules per mole. So it is, in fact, positive because this reaction is not spontaneous, as written. So what would K be at this temperature? But just based upon delta G, if this reaction's not spontaneous, is K going to be a big number or a small number? Small, yeah, because we're going to stay on the reactant side. So now, since we have delta G, we did the hard, heavy lifting already. We're going to use the equation delta G equals negative RT ln K. Right, we already have delta G, so 228.9 times 10 to the 3 joules per mole equals negative 8.314 joule mole Kelvin. Temperature is 298 ln K, and so we just solve for K here. All right, so this is kind of crossover with thermodynamics and K, relating it to delta G. All right. Yeah, teaching 1220 is like it's like K. We just talk about big K for like a very long time and see where it comes up constantly. So in this case, K is related to electrochemistry. And then you solve for K. K ends up being a small number. It is 8.44 times 10 to the negative 6. So that makes sense that this reaction at equilibrium is going to stay primarily on the reactant side because it's not very spontaneous. All right, what is the value of E cell if we have these concentrations? So this is E cell. I don't have the not there. Is that a mistake? Did I just forget it? No, we need to use what equation given this information? The Nernst equation, yeah, because are we at standard conditions any longer? No, we're not. That's why the not isn't there, and that's why I give you different concentrations. So we're going to use the Nernst equation, which is E cell at any non-standard conditions, is equal to your standard cell potential. So we still need that value that we calculated earlier. Is it minus? Yeah. 0.0592, yep, volts over N log Q. So we just need to figure out what Q is. We know that N equals 2. We got that earlier. And we know E cell. So we just need to get Q. So Q is just like K that we've talked about before. It's products over reactants. I will point out there was a homework question where you had to do the Nernst equation, calculate Q, but there was things that were aqueous and gases. And so in the Nernst equation, since everything is referenced to table values, if you have things that are aqueous, you keep them in molarity when you do Q. when you have things that are gases with pressures, so I think the example was like pressure of O2, you're actually allowed to keep it in ATM, right? So that's a small detail with Q in the Nernst equation and Q when we did thermodynamics, because everything's referenced to standard conditions where things that are aqueous are molarity, things that are gases are ATM. When you calculate Q, keep gases in atmospheres, and that's okay. All right, and that's how you get the correct Q. All right, so Q in this case is, we have to go back and look at the balanced redox reaction. Thankfully, this is already balanced for us. So it's lead concentration over nickel 2+ concentration. So we see that Q here is equal to a tiny number. It's whatever that is. What is Q? It is equal to 0.01 over 5. So it's equal to 0.002. Right? And that's the value that we're going to put into our Nernst equation. So let's put it all together. Negative 0.15 volts minus 0.0592 over 2 log 0.002. There we go. And then we get that our cell potential here at these different non-standard concentrations is negative 0.07 volts. So even at these concentrations, this reaction's still not spontaneous, but we're getting close. We're getting close. All right. All right, so that's pretty much as hard as it gets with electrochem. And then the last thing we talked at the very end with electrochem was electrolysis. That, yes, this reaction is not spontaneous, all right? But how can we make this reaction go? If we supply it electricity, and that's what electrolysis is, forcing non-spontaneous reactions to go by plugging it into a wall socket. And so in this example, this last one, how long will it take to consume 1 gram of lead at the anode if electricity is supplied at a current of 1.5 amps? And so when doing electrolysis, I just always remember an amp means what? A coulomb per second. So 1.5 amps actually means 1.5 coulombs is supplied every 1 second. All right? So we want to consume lead. So in a redox reaction, if we have lead solid, what does it become? Lead 2+. Yeah, so how many electrons are required to do that? 2 electrons. So I want to start with 1 gram of lead, and I need to figure out how many electrons I need to make that happen. So 1 gram of lead, oh, I didn't give you the molar mass. Man, we haven't done that in a long time. So what's the molar mass of lead? 207. 207.2. Okay, grams is 1 mole of lead. All right? You told me that this process, just like any balanced reaction when we do stoichiometry, takes 2 electrons. So for every 1 mole of lead that I'm consuming, I actually need 2 moles of electrons. All right? And now I'm in moles of electrons, and so Faraday's constant is what allows me to relate how many electrons I have to its actual charge that I can use the current that's given here. And so remember, Faraday's constant is 96485 coulombs per mole. So that means for every 1 mole of electrons, I need to deliver 96485 coulombs of juice. All right, and then now this is where my current comes into play that's given. So for every 1.5 coulombs, 1 second goes by. And then that gives it to me in seconds. How long does it take? So technically I didn't say what unit, so I'll just keep it in seconds. So here, I think if you calculate it, it's 620 seconds. So like 10 minutes. Okay, so plug this in the wall for 10 minutes and your lead anode should decrease by mass about 1 gram. All right? And so the tricks here for electrolysis, know how many electrons are transferred during the event. The most common mistake I see is students forget this step, right? They just assume it's 1 electron, but it depends on the charge, right? I think when we were talking about aluminum dioxide or aluminum oxide, so like Al2O3, all right? So that's the most stable form of aluminum. That's what we mine out of the ground. But aluminum foil is aluminum solid, right? So how many electrons are required to reduce 1 mole of aluminum? So we look at oxidation numbers here. So aluminum solid has an oxidation number of 0, but the aluminum in aluminum oxide is actually +3. So this is a 3 electron event. For every 1 mole of aluminum, you need 3 electrons, right? So it's all about the charge and the balanced redox reaction. Okay, good. All right, that's electrochem. All right. Okay, so what are we going to do now? What chapter? What chapter? 21? Wait, 21, not 23? We're good with 23? Okay. Actually, let's just quick go over oxidation state and coordination numbers. So this is number 8. Okay. So oxidation state of the metal. I want you to tell me the oxidation state of the metal and the coordination number. So oxidation state, it's essentially charge. So we need to know what are the charges of common ligands and what kind of dentate is it? Is it a monodentate? Is it a bidentate? And so I have a list of ones that I want you to memorize. I think I have it in the note in the key of which ones to memorize. Like, do I have it here? Practice, Zoom, key, okay, yeah. Here. So these are the common ligands. All right, common neutral ligands are water and ammonia. Boop, there we go. Also, ethylene diamine is a common neutral ligand, but it is a bidentate, all right? Versus common charged ligands, these ones are monodentate. So chloride, fluoride, cyanide, hydroxide, thiocyanate are all charged ligands, and that helps us get oxidation number. And they're also monodentates, and that helps us determine coordination number. Again, coordination number is not number of ligands around it, it's how many bites, how many bonds to the metal center. So silver is bonded to ammonias, so, and the overall charge of the complex is +1, so that means silver is also +1, because ammonias are charge neutral. What is the coordination number here? 2, yeah, because both of those ammonias are bidentates, or monodentates. What about this cobalt? Cobalt has a coordination number of 6, yes, because there's 6 ammonias. Those chlorides aren't in the coordination sphere. They're just there to tell you what the overall charge is of the complex. So chlorides are negatively charged, so that means the whole complex is actually +3. So that makes cobalt +3 as well, because ammonia is charge neutral. All right, cobalt ethylene diamine. What's the charge of cobalt? +3 again, yeah, because ethylene diamine is neutral. Chlorides are -1, but there's 3 of them. Coordination number here, is it 3? No, it is still 6, because ethylene diamines, I like to think of it as 2 ammonias just tethered together. So if you have 1 ethylene diamine, you actually have 2 ammonia bonds to your metal center, right? Because ethylene diamine is a bidentate. All right, what about this compound? What is the charge of cobalt? +2. So remember, ethylene diamine is neutral. There's 2 chlorides, so there's a total of a -2, and then there's 1 bromide on the outside, so -1. So cobalt is again +3. Yeah. So we do care about the things that are on the outside if we're doing oxidation number, but we don't care about the things on the outside if we're doing coordination number. So what is the coordination number here? It is 6 again, yes, because ethylene diamine bites twice. There's 2 of them. And then there's 2 chlorides. I actually think I have this compound as a picture down here. It's basically this one. 2 ethylene diamines, 2 chlorides. There are 6 fights around the chromium. All right. Okay. So let's keep going. All right. This cobalt, what do you think it is? It's +3 again because 1 bromide, 2 nitrate. So cobalt's +3. Coordination number 6. Yes, 6. Okay. Platinum. This is platinum 4+ because there's 4 chlorides. And the whole thing is neutral. What is the coordination number? 6. Cool. Tin. Okay, so there's 2 sodium, so that's +2. There's 6 chlorides, so that's -6. All of it's charge neutral, so tin has to be +4. And the coordination number? 6 again. 6 is the most common coordination number, yeah, octahedral. Right? So those sodiums, again, do not count towards the coordination sphere, the coordination number. All right, last one, manganese. So -6 +4, manganese is +2. Coordination number 6, again. Okay, cool. All right. My favorite game, what are these? What kind of isomers are being depicted? The more you look at, then the more you'll be comfortable with it. All right, so we've talked about a lot of different isomers, coordination sphere, linkage, geometric, and then probably the hardest one, optical isomers. And then sometimes I trick you and I actually show you the same molecule, just in different perspectives. So it's like playing the game. How are these compounds different? And yeah, so it's 6 in trans. I don't know, I have to look. I have to figure out how it's different. So I think it's the ammonias. Yeah, there we go. 2 ammonias right there. And then the ammonias are right there in the other molecule. So these are cis and trans isomers. All right, so they're geometric isomers. All right. Do these molecules have different properties? Yeah, they do. They're different molecules. They have different names. Yeah, cis and trans. Remember when we talked about cisplatin and transplatin? What does cisplatin do? Kills cancer. What does transplatin do? Nothing. All right, the next one. How are these different? Did you? They are linkage isomers, yes. Because how are they different? Yeah, SCN is there, but you might be like, oh, but SCN's right there too. But how it's written is trying to show you, hey, your metal is bonding with the sulfur in thiocyanate while it's bonding with the nitrogen in this one. So these are different. They have different properties. With linkage isomers, the bonds are in fact different. So these are linkage isomers. All right, these. Yeah, I'm trying with this board thing. What am I trying to tell you? That I'm taking the mirror image. You're looking at the 2 mirror images. So are these different molecules? Yes, they are. What's the trick with tetrahedrals? 4 different things will always be chiral. Yeah. So these are they're mirror images, but they're optical isomers. All right, they are, meaning they're different. They're different. Okay. Yeah, those are optical isomers. All right. What about these? They're mirror images too, right? So they're optical isomers? No, they're not. They're not optical isomers because this carbon is not chiral. That if you take the mirror image, you actually get your same molecule back. You might be thinking, oh, but these 2 hydrogens, they're pointing the other directions. Just rotate it in your mind. And you'll make both of those molecules look the exact same. So these are the same molecule. And the reason I know that is because you have 2 hydrogens there. Once it's not 4 unique bonds, then it's never chiral for a tetrahedron. All right, okay, good. Okay. This is my favorite thing to do. I do this. I say, is this molecule Is this molecule chiral? No? 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 Is this, well, one, is this molecule flat? No, just because I drew it flat doesn't mean it is flat. Yeah, yeah, so chemists, we're lazy. Sometimes we don't want to draw the wedges and the dashes, but what is the central atom here? It's a carbon atom. Carbons with 4 bonds are always tetrahedrons. All right, so just because I drew it flat doesn't mean it is flat. All right, so yes, this is a chiral molecule. All right, because this actually doesn't exist. It does, in fact, look like a tetrahedron where you have A, B, C, D, and when you reflect that, do the mirror image, it is, in fact, a different molecule. It's chiral. All right, so just because it's drawn flat doesn't mean the molecule's flat. Okay, carbons with 4 bonds, always tetrahedrons. Okay. So chapter 23 homework is due on Sunday, right? I think there's a question in the homework that asks for regular objects if they're chiral or not. Did you run into that question yet? Yeah, so like the first one is like a slice of bread. Is a slice of bread chiral or not? No. What's the trick to figuring out if something's chiral? If there's a mirror plane in the thing, when you take the mirror image, you will get the same molecule back. So I asked myself, does bread have a mirror plane in it? Yes, it does. It does, because it's like a flat, right? It's like a pancake thing. Yeah, so this is not chiral. What were some of the other examples? Yeah, so someone asked me that. I was going to bring that up. So I don't play golf, but I do believe fancy golf clubs, there are left-handed and right-handed golf clubs, okay? All right? See, that's not super inclusive because I've never touched a golf club. Yeah, so a golf club, I think like the fancy ones they use, right, like the putter thing, you can only putt off of one side. So there's a left-handed and right-handed set of golf clubs. But see, me, I was talking to Myra earlier, like we go like mini golfing, where all of the clubs, you can actually putt off of both sides. So is a mini golf club chiral? No, there's actually a mirror plane in it, where it's just simple enough that they make it so, you know, you can putt off both sides. But a like nice, I don't know, how much does a thing of golf clubs cost? Too much, yes. All right. So since it costs too much, yes, they do have unique left-handed and right-handed golf clubs. But here's this. How about a baseball bat? Is a baseball bat chiral? No, yeah. Is there a left-handed, right-handed baseball bat? I don't think so. Also, think about what a baseball bat looks like. It's actually cylindrically symmetric. Yeah, so it's not chiral. I don't know. Are there left-handed and right-handed baseball bats? I don't think so. You can bat left-handed and right-handed, but you use the same bat, right? Yeah. And then the last one was a screw. Someone asked about a screw. Is a screw chiral? Yeah, so here, what's the saying with, like, have you ever, like, tightened something? What's the saying? Lefty loosey, righty tighty. So if you take a mirror image of a screw, is righty tighty, lefty loosey still valid? No, it's not. So that means, is a screw chiral? Yes, it is. It's chiral. If you take the mirror image, now it's going to be righty loosey, lefty tighty. And there's actually some things out there that actually are deliberately reverse threaded. Yeah, so like I've used like very dangerous like hydrogen tanks because they're explosive, and they are deliberately reverse threaded because they're forcing you to like think about what you're doing because you're working with like explosive things. So those are deliberately reverse threaded. Yeah, instead of like lefty, like 99% of the time, lefty loosey, righty tighty will get you out of a lot of jams, but sometimes things are reverse threaded. What were other examples? Or are those the weird ones? Those were the weird ones? Okay, good. Okay. Oh, perfect. This one, is it, what are these? These are optical isomers, yeah. So in the key, you'll see that I say, oh, these are delta lambda optical isomers. And what I'm just trying to tell you is that these mirror images are different. How the paddles are rotating are different. One is in the delta orientation, one's in the lambda orientation. You don't need to be able to identify which one's which. I just want you to know that these molecules are in fact different. And so we find optical isomers in like carbon tetrahedrons. We see them in octahedrons that have paddles in them. Like I like to think of them as propellers. Propellers only work in one direction. That's why they're chiral. So these have the 3 paddles. These are different molecules. If you care which way they're going, I think this one, the blades are turning, or like they're oriented this way. But in this one, the blades are oriented that way. All right, so they are different. This is the pinwheel example. I showed you the pinwheel. That is a chiral object because we can only blow on the pinwheel one direction to make it spin. All right, these. They are also optical isomers for the same reason as the previous one, but the only difference is that there's just a missing propeller, all right? So like these ones, it's like a 3 propeller fan. This one, I just plucked off one of the propellers and replaced it with 2 chlorine atoms. But you can just think of that as like the 3rd propeller, right? So like 2 or 3 paddles on a octahedron will make something chiral. But I think is the next example, yes, this one. So this, yeah, these, you might be thinking, oh, these are paddles. They're optical isomers, but they're not. They're geometric isomers. They're cis and trans isomers. So what I want you to focus on are these cyanides. See, these cyanides are across from one another. These ones are sisters. So these are cis and trans isomers. All right. But you might be thinking, oh, but there's paddles, so it's optical. Nope. And let me just expand on this one a little bit more. Only one of these isomers is chiral. Which one is it? The cis one is chiral, yes. That we could take the mirror image of the cis version and we would get a brand new molecule. But if we took a mirror image of the trans one, would we get a brand new molecule? Nope, it's the same molecule. The reason is the trans molecule has a bunch of mirror images in it, or mirror planes. You can see one right here. There's one kind of on the square that's here. If you take the mirror image, you get the same molecule back. All right, these 2 molecules. They're mirror images, but they're the same molecule. Again, because the one molecule has a bunch of mirror planes in them. When you take the mirror image, you get the same molecule back. Same. These 2. Just try to name it, I guess. Yeah, so this one's tricky. These are the same molecule as well. Because in one of them, yeah, it's just rotated. But some people have trouble seeing it. What? Yeah, so look, these CNs, they're what to each other? Across. What about these CNs? No, see how I wrote it in such a way where it's CN? See how it's still a carbon chromium bond? Yeah, that's deliberate. Yeah, it's the same molecule, I just rotated it. Think of it like these CNs, it's like north and south, right? And it's like north and south this way. But in this molecule, I'm rotating it so you're looking like down this north-south axis. Yeah. Hopefully if you're a dentist out there that you can see this in your head. What's up? This one? Yeah, you're right. If I didn't write NC here, if I did write it CN, which implies that you have a nitrogen chromium bond, that would be a linkage isomer. Yeah, that's right. But cyanide does not do linkage isomerism, I think. So yeah. Okay. Yeah, it's tough to see these things. Yeah. So like if I had this, okay. Okay, if I had like doot, 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 what kind of thing is that? Face or fash or whatever. Yeah, face. There's like face and mer. Face is when all three ligands are on like the same face, and like you could rotate it and have it stand on a table. So if I had this molecule and I compared it to this molecule, what are those? But I thought the isomer, they're face and mer, so the other one has to be mer, right? No, I just drew the face version twice, just with the three same ligands in a different place. You can just rotate these two molecules, and they are actually the same molecule. Yeah. I helped a friend like study for the DATs, the like MCAT version of like the dental exam things, and their questions are real cool. They have like a section of like spatial awareness where it was like a picture of a blocks from one like perspective, and they asked you what does the pile of blocks look like from above. Yeah, that was on their MCAT, like the dentist MCAT, and I thought that was cool. Right. And so yeah, this spatial awareness stuff important for dentists. Oh, look, here are face and mer stuff. Yeah, these are face and mer. Face, mer, where these three ligands are the same, oriented in a certain way, and then that is mer. Okay. I remember it that these three, they lie on a face that I could rotate it and it could lay on the face of like a table. These ones, I memorized mermaid tail, and it looks like a mermaid tail. But you can think, I think that word comes from meridian, like on a globe, where the meridian is like this, I think, on a globe, right? I don't know. All right, what are these? Are they cis and trans? No, they're not. They are the same molecule. Yes, they are. But, oh, they're not optical isomers, but they look like mirror images, right? No. Yeah, so since it's symmetric, this is a flat molecule. Since this is platinum, it's not a carbon atom. These are the same molecule, even though I drew mirror images. Yeah. Or you can think of it this way. This is transplatin, right? Those chlorines are trans to one another. What about over here? They're also trans, so it's the same molecule. Yeah. Okay. All right, what do we want to do next? I did not make a Kahoot. I know. I got lazy, so I didn't make a Kahoot. We'll just do 21, okay. Okay, good. We'll go in order, and then we'll just pick up at 2 o'clock. I'll post everything. Okay, all right. Write a balanced nuclear decay equation for the following. So, two things. You just have to memorize what the radiations are, and you got to do reading comprehension. So if a beta is being emitted, the beta particle is a product. So let's just go over the types of emission. We have beta, that's 0, -1. Alpha, 4, 2. What else is there? Positron, 0, +1. And so these charges, I'm not meaning like balance the number of electrons, no. So finally, in nuclear chemistry, we can ignore overall charge. We are just balancing mass number and like number of protons and stuff. So we're not actually balancing the electron clouds like we've been doing all this time. What else is there? What? What is it? Oh, gamma. Yeah, but who cares about that? Yeah, gamma. It's just high energy, so it has no weight. All right, beta emission of copper 66. So copper, all right, so I tell you it's copper, so the number of electrons are implied, so 29. And then 66 is the number of, is the mass number, okay? So that's how you need to figure out, okay, how many protons are there, then that gives you how many neutrons are there. And so beta particles being emitted, so I know that one of my products is that. And so you balance it. So 66 is still the mass number, but now the number of protons is 30. Is So that's a zinc. Right? Same thing, but now we're emitting an alpha particle. So it's still copper 66. Right? Alpha particle is this. It's being emitted, so it's a product. And so my missing piece is 62, 27. What's that? Cobalt. There we go. And so you can check yourself, add up all of the number of protons and the mass numbers on both sides, and they should match each other on each side. All right, positron emission of iron 53. So iron 53, iron, where are you? 26. So positron emission, so same thing. Our positron is a product. And so what's the missing piece? 2553. So manganese. These are fun. All right, last one, electron capture. So my electron is actually a reactant, yes. So it's funny, you know, when we think about a substance gaining an electron, we usually think about it turning into an anion, right? Like, you know, we have some element, we add an electron, and it becomes X minus. That's chemical reactions, like electrons. But remember, nuclear reactions, we're not caring about the overall charge. This electron is being captured into the nucleus. And so what happens is, I think what a proton is converted to a neutron when that happens. So this is different than like an anion being formed. So calcium, 38, 20 protons is capturing an electron. The nucleus is capturing an electron. So my product is 19 and still 38. So this is a potassium. Okay, cool, there we go. So just do reading comprehension. All right, let's balance the following transmutations. So again, with all of these, we don't care about charge. We just want to make sure the mass number and number of protons match on each side. So I just take inventory. So there's 31 mass number, 15 protons. So that means the missing piece here has 30 protons and 15 protons, right? So what is that? Phosphorus, cool. Okay, the next one. So again, just take inventory. 243, 96. So our missing piece is, has 2 protons and 4 mass number. So what is that? That's an alpha particle. Yeah, cool. All right. Yeah, that's fine too. But remember, I never ask you to write anything on the exam. Yep. Okay, so do the following nuclei lie on the band of stability? How would you expect them to decay? So I give you 3 different examples here, and I give you the band of stability, but technically you don't need this graph to answer these questions. I just give it to you so you feel confident, but you don't technically need it. So let's look at these. So what are the 3 rules for predicting nuclear decay? If our neutron to proton ratio is too high, what's going to happen? Is it beta? Beta, yeah. Beta emission happens. If your neutron to proton ratio is too low, what happens? I think it's positron, right? And then the last one is if your number of protons is above bismuth, so if it's like 83 or above, then it's automatically alpha. And those are your rules. So we just have to look at these substances and predict. So potassium, 40. So potassium has, so we need the neutron to proton ratio. So there are 19 protons and 21 neutrons. And so mathematically, that is 1.11. So what do you think? It's probably too high. 1 for light elements and Potassium is fairly light. 1 is the preferred neutron to proton ratio. So what's probably going to happen is beta emission. But for funsies, let's actually just predict what is the product if potassium 40 undergoes beta emission. So 40, 19, potassium. If we emit a beta particle, what's our product? 40, and then this is 20, and that's calcium. What's the neutron to proton ratio there? 1, and that's real good, real stable. Okay, yeah. So yeah, that's why this undergoes beta emission. Beta emission will lower your neutron to proton ratio, while positron emission raises it. So hopefully we have an example there. All right, plutonium 244. Do I need to actually calculate the neutron to proton ratio here? No, because which one does this fall under? It's alpha because it's real heavy. All right, so plutonium is 94 protons, so it's automatically going to undergo alpha emission. Does not include bismuth, yeah. Because bismuth is the heaviest stable element. Okay. Oxygen 14. So this one is not the 96 or 93 rule, so we actually do have to calculate the neutron to proton ratio. But since there's 3 examples, we probably know which one this is. It's probably positron, but let's check. So oxygen has 8 protons, 6 neutrons because it's 14, a mass number of 14. So this is way too low, 0.75. All right, so if your neutron to proton ratio is way too low, like below 1, then you're most likely going to have positron emission. All right, but let's check. Let's see what happens when oxygen 14 goes under positron emission. So 14, 8, what's the product? 7, 14, what at? Nitrogen. Is that nitrogen stable? Yes, it is. It's 7, 7, 7. Also, look at nitrogen. It's like, its molar mass is 14. So nitrogen 14 is the most common isotope. All right. And I like, I think we already did this example, but I like to do it again. When we think about like carbon dating, we're using carbon 14, which is it's an isotope. It undergoes decay. But I don't know, for the longest time, I always, before, I started thinking more deeply about nuclear chemistry, if you think about carbon 14 and, how in dead stuff it decays, I don't know, for the longest time, you'd think that carbon 14 decays into a more stable form of carbon, like carbon 12, but it doesn't. If we apply the neutron to proton ratio here, we see that carbon 14 has a neutron to proton ratio of 6/8. So this is actually really high. It's like 1.2. So carbon 14 actually undergoes, what is this? Beta decay, right? So beta decay, if we have carbon 14, so 6 electrons or protons. If we have beta decay, what's the product? Other product, it's 14, 7, so nitrogen again. So I always thought that was interesting. I don't know, for some reason, and it's based upon nothing, that you'd think that carbon 14 decays into a more stable form of carbon. It doesn't. It actually decays into a stable form of nitrogen because of the beta decay that it undergoes. So I don't know if that's interesting to you, maybe. Yeah. Okay, all right, so thorium 232, its decay chain starts off with an alpha emission, 2 betas, and then 2 alphas. What nuclei is formed after these 5 steps? Do you want to do it the long way or the quick way? The quick way? Yeah, so if we're doing alpha and beta emissions, that means that these particles are reactants or products? Products, yeah. So if we just add up the weights of all of them, we can just rip them all off at once instead of one at a time, right? Because after each emission, there's a transformation happening. But we don't really care about the middle ones. We just care about the end ones. So let's just rip them off all at the same time. So there's an alpha emission, right? Then there's 2 beta emissions. So beta is -1. and then another beta emission, and then 2 alphas, so 4, 2, and another 4, 2. So let's just add all of that up. This substance is going to lose a total of mass number of 12, but how is its proton number going to change? So 2, 0, 2, so 4. So that's the weight of everything that's lost as a product, all right? So I'm just ripping all of them off at once. I'm just adding up everything and taking them all off at once. So we have thorium 232, so thorium is 90, all right? So we're doing our alpha, 2 betas, an alpha, and an alpha. What is our product that has to be balanced with a mass number of 12 and 4? It will be 220, I think, and what is that? 86? What is that? Radon. Is that what my key says? Heck yeah. And if you look at my key, I do it one at a time. I do each one at a time. But technically, you don't really need to. You can just rip them off all at once, okay? Because I don't really care about those intermediate steps. And since we know that mass number and number of protons, all of those balance, we can just do it all at once. Okay, all right. Okay, last one's here. Half-life stuff. So this is review, chapter 14. Oh, crap, I forgot to post the results. The last survey was what chapter do we think is the hardest in this class? 17. A lot of people said chapter 14. Yeah, kinetics. I don't know. So thankfully, the end of nuclear chem is just kinetics review, where what are all radioactive decays? They follow first order kinetics, where we now use the term half-life a lot more because that number makes a lot more sense to us. So half-life is natural log of 2 over K, your rate constant. Rate constant is related to our integrated rate law. Natural log of concentration at some time is natural log of your junk initially minus KT. So both of those are related. So here I tell you that the half-life of cobalt-60 is 5.3 years. So that's T1 half. What fraction of a sample of cobalt remains after 8 years? So this is T. What a lot of students try to do is they try to stick 8 hours in the T1 half equation. Okay, the point of this T1 half equation is to convert K into a friendly number that makes sense to us humans. So I'm going to use that half-life value to calculate K that I can then use in the integrated rate law. So let's get K. So 5.3 years. Move things around. So K is equal to 0.693 over 5.3. And so I get that K is equal to 0.1308 year to the negative 1. I have no idea what that means. I understand a half-life of 5 years. That makes sense. But 0.108 years to the negative 1, that's the rate constant. Not as useful to me, but we can still put that K into the integrated rate law, and that's what we want to use. We're going to stick that value into there. So I'm just asking what fraction of your sample remains. So I'm just going to say I begin with 100% of my stuff, and I'm going to solve for how much I have left. So natural log of A sub t equals natural log of 100 minus that 0.1308 years to the negative 1 times the 8 hours or 8 years that actually have elapsed. Okay, so but before we get our answer, let's just use our intuition. The half-life is 5 years and 8 years goes by. About how much will we have left? A little bit less than 50%. So hopefully our answer is a number less than 50%. Okay, all right. So you do that, you get natural log of A sub t equals, okay, natural log of 100 minus 0.1308 times 8. 3.56, so e to the both sides there. So I get that a sub t equals 35.1. And so I kept this in percent, all right, because I did, 100, so now it's 35%. So does this answer make sense in the context of what was given? Yeah, that half-life is 5 years, but 8 years goes by, so it's not quite 2 half-lives, but more than 1, so 35% does make sense. Okay, good. All right. And remember, reading comprehension. If I could ask how much of your sample was lost, yeah, you would still do all the same work, but you wouldn't report 35%, you would report 65% or whatever. Yeah. Okay, right. Yes?
For the proton neutron proton ratio, the like if it gets heavier, like the element of like more than one.
Yes, so once your elements get, so I think calcium is the heaviest element that still has a stable 1-to-1 neutron to proton ratio, right? And then once you get heavier than that, then the most stable neutron to proton ratio does become higher. So if we look at this table thing, iron, its stable neutron to proton ratio is 1.1. And we get to iodine, it's 1.4. Then we go to the heaviest bismuth, and it's 1.5. So the idea here is if I have a question on an exam and I don't give you this graph, I will make it very obvious if we are too high or too low. It's going to be very obvious. All right? If not, if you can't answer it like that, then I will give you this table. So if we did it in such a way, where's cobalt? Cobalt is 27. So for funsies, let's predict, so cobalt 60. What kind of decay does cobalt 60 undergo? So cobalt 60 has 27 protons, so its neutron to proton ratio is 33 over 27. So what is that? 33 over 27. 1.22. So this one, it would probably make more sense for me to give you this graph because cobalt is heavier. So based upon using this graph of where the stable neutron to proton ratio is, cobalt with a ratio of 1.22, is it too high or too low? Look at where it's close to. Cobalt's probably closest to what label on this? Iron, yeah. Cobalt's 27. Iron is 26 protons. So am I too high or too low? Too high, yes, too high. So what's going to probably happen? Beta. Yeah, so you could answer this one, but I would have to give you the graph. If I give you the graph, it'll be in the question. But usually it's obvious. Like, for example, oxygen. That one's obvious, I feel, right? Or this potassium example is kind of obvious too, because it's a lighter of the elements. It's still above that stable 1-to-1. All right, good. All right. But in the end, it's just a 50-50 guess, right? It's a 50-50 guess. All right. Wonder if there's another way you could do it. Or you could do it this way. Look, okay, so cobalt 60 has like a molar mass of what? Weighs about how much? 60 AMU. Look at the most stable cobalt. The most stable cobalt weighs about 58, 59. So that means this cobalt has too many neutrons. It's too high, right? That it would rather be closer to what that stable molar mass is. Or if we looked at the potassium example, we did potassium 40, but what is the most stable potassium? It's actually 39. Again, too high, too many neutrons. What is the most stable oxygen? 16. But this oxygen is 14, so we don't have enough neutrons, so it's too low. So that's another way you could do it without using the table. Yeah? If you want more assurance, I think that's what you're looking for. You're looking for assurance that you'll be right and and recognize, am I too high or too low? The periodic table can help you too, because those ones, those masses are stable. That's why those numbers are there, because they come from natural abundances. All right, finally, let's do the last one. A certain radioactive sample reduces by 35% after 2 days. What's the rate constant? What's the half-life? What percentage remains after 1 week? Okay, reading comprehension. So if the sample reduces by 35%, that implies A sub 0 equals 100 or 1. But then A sub t equals what, 35? Nope, 65%. All right, after 2 days, so that's t. So that's all the information we need for the first order kinetics rate constant, rate law. So ln of A sub t equals ln of A sub 0 minus kt. So put in the numbers. So ln of 65 equals ln of 100 minus k, that's what we're solving for, times t, so 2 days. So that means when we solve for k, our answer will be in days to the -1. And so let me prove to you I know how to do math. So k 2 days. So isolating k, this will equal natural log of 100 minus natural log of 65 over 2 days, I think is how we get it. So natural log of 100 minus natural log of 65. I think you can also divide the numbers. Yeah, but I'm not like really math fancy, so I'm gonna not do that. Natural log of 65. So what I think this numerator simplifies to is natural log of 100 over 65. Got it? Yeah? Okay. I don't trust myself to get that right on the exam. I'll just do it written as is, so yeah. All right, there's that over 2 days, and so that will give me k, my rate constant, 0.215 days to the -1. I have no idea if that's fast or slow. I don't know. So that's why the T1/2 equation puts it into better human perspective. So T1/2 equals natural log of 2 over that k we just got. So natural log of 2 divided by that. This makes sense. My half-life is 3.2 days. Right? You lose half your junk in 3 days. That makes sense. And so the last question here is, what percentage of your sample remains after 1 week? So what do we think our answer will be around? About 20, like it's a little bit more than 2 half-lives. So 50%, 25%. Our answer is probably going to be a little bit less than 25%, but let's check. So how's the best way to do, what do you think the best way to do this is? Use the integrated rate law again, all right? Use that k value you just got earlier, so natural log of A sub t, that's what we're solving for this time. So natural log of 100 minus k, so 0.215 days to the -1. But this time 7 days. All right, and so we get that, did I write this down? Yes, that A sub t after 7 days is 22.2%. Wow, look at that. Look at that. I think this is another way to do it, all right? So we know that T1/2 is 3.2 days, but if 7 days goes by, divide by 1 half-life, is 1 half-life. That means 7, I think this should work, 7 divided by 3.2 days. That means 2.1875 half-lives have gone by. So if we take 100%, multiply by a half, that's 1 half-life. But we need to do it 2.1875 times. This, I believe, will get you the same answer. Let's see. 100 times 0.5 to that number. It's a little bit off, 21.9, but yeah, it rounds to 22%, so you get pretty close. All right? Okay. 20 minutes left. Okay, we'll spend a couple more minutes doing whatever question you have for old stuff, and I'll blow our big K stuff up. Let's talk about big K. Yeah, let's do some big K stuff, and then we'll blow it up. So let's do midterm. Let's do number 25. Big K, equilibrium constant. Yes. Okay, let's calculate the equilibrium pressure of S2 gas at equilibrium when we start with 4.2 atm of H2S gas. So I give you Kp, so I give you big K, I give you initial concentrations, so we want to calculate equilibrium concentration. So we need to draw out an ice table. So all of these equilibrium questions really should start with an ice table. Just want to remind ourselves how to do these, because for the longest time we've been doing weak acid, weak base ice tables, and everything's been a 1-to-1-to-1 ratio. So I want to remind you how to do equilibrium here. All right, so this 4.2 is going to go in my initial line, so it's going to go right here, 4.2 atm. But I have 0 of all this stuff. So which way does my reaction have to go? Forward. So what goes in the change line here? Minus 2x. Yes, remember we've done a lot of weak acid, weak base, and it was always minus x plus x. But look, we always have to follow stoichiometry. That was chapter 15. So this is minus 2x. And then what's under H2? Plus 2x, and then plus x. So at equilibrium, we have 4.2 minus 2x. 2x of H2 and x of S2 gas. What's the trick with ice tables? The E line always goes into the K expression. But let's remember how to write a K expression. It's products over reactants, but we need to also include the stoich as the exponent. So the K expression for this reaction is partial pressure of H2 squared, because of that 2, times the partial pressure of S2 gas over the partial pressure of H2S gas, but it is squared. Yes, squared. So we got to include those coefficients, right? And then these x's are what go into the equilibrium line, all right? Okay, so the coefficients kind of show up in 2 places. They show up in the E line when we do our ice table, but they also show up in the exponent. So let's put this together. So Kp equals 2x squared x over 4.2 minus 2x, that whole thing squared, equals, and I tell you it's 2.2 times 10 to the negative 6. And so since we're calculating the E line, this is what I called the type 2 ice table, where we might have to make an approximation. And we probably do want to make an approximation here, because this, I think, reduces to 4x cubed over 4.2 minus 2x squared. So this is quite difficult to solve yourself, so I would probably make an approximation. What approximation do you think we'll make? Yeah, get rid of that minus 2x. We can do this. The reason is because this reaction is primarily on the reactant side, so the amount of products we actually make, the amount of minus x, 2x here, it's going to be a really small number in comparison to 4.2. So that's why we can make the approximation. Right, and so then this reduces to 2.2 times 10 to the negative 6 equals 4x cubed over 4.2 squared. Does this require any major math? No, it's just like you move things around. So 2.2 times 10 to the negative 6 times 4.2 squared over 4 equals x cubed. I think that's what it is. And so you get that x cubed equals 9.7 times 10 to the negative 6. And so to undo that cube, we take each side to the 1/3. And so we get that x equals 0.021 ATM. Okay, so we got x, but is x my answer? I don't know, because what is the question ask? What is the equilibrium pressure of S2? So what is that in terms of x? It is x. So is x my answer? Yes, it is. It is my answer. And so we're right that x is real small. X is 0.02 ATM. That's what x is. So we were right in making the approximation that we're saying x is really small. It's not going to change this pressure, this 4.2 value, very much. It's only going to change it a little bit in that last significant figure. So if this question asked for equilibrium pressure of H2, we would have to double that x value because that's what the ice table says. Right? Okay, so let's do one more here. Let's predict what kind of reaction this is given these observations. So this is Le Chatelier's principle, but I'm telling you the observations, okay? The predictions, you need to tell me what reaction matches this, okay? Because I think it's easy enough, more common Le Chatelier's is like I give you a reaction, I say, oh, you heat this exothermic reaction up, which way does it shift? Or you add more reactant, which way does it shift? This kind of more like your lab. You use your observations to figure out what reaction it is. So the reaction is heated, more reactants are formed. What does that imply about my reaction? It's probably exothermic, yeah, because if we have reactants go to products, where do you put triangle to make more reactants? It has to be on the product side. So that's an exothermic reaction, so we can eliminate some of them. Right, so it's exo. The volume of the reaction vessel halves, more reactants are formed. So if we are squeezing our reaction vessel, what are we doing to the pressure? It increases. And so if more reactants are formed, what does that imply about the number of gases on the reactant side? There's less gas on the reactant side, less gas on reactants, because when we squeeze on the reaction and it relieves itself by going to the reactant side to relieve the pressure, it implies there's less gas. So I think, what's the answer? C. C. Okay. I'm getting tired, so let's do one more and then we'll blow stuff up and then we'll come back here too. Okay. Is there a certain kind of question someone wants me to do right now? No? Do you just want to blow stuff up? Oh, yeah, yeah. The activated, yeah, what question number is it? Oh, it has to be in this packet. What do you mean, activate, like, what is it? Oh, yeah. Are you going to be at the review session? Yeah? Okay, give me some time. I'll think about an example and I can, yeah. Yes? Oh, yeah. Okay, so when we have magnets. Okay, so paramagnetism. Okay, let's just go to an example because I think I skipped it in chapter 23. So here, which of the following substances is predicted to respond the most to an external magnetic field? So this question is asking what substances are paramagnetic. So substances with metals that have unpaired d electrons are paramagnetic. They will respond to a magnetic field. We did the example, do you remember, where I had the things on a string and I used magnets and it moved them, right? So the presence of unpaired electrons will allow metals to respond to a magnetic field. So D shells D subshells have 5 orbitals. And so remember, following Hund's rule, when we add d electrons, so 1, 2, 3, 4, 5, 5 d electrons has 5 unpaired electrons. But once we go to 6 d electrons, now we start pairing things. So this substance is still paramagnetic, but less so. Versus if I have 7, less paramagnetic. Versus I am a fully filled D shell, this is not paramagnetic. So D10 is not paramagnetic. D0 is also not paramagnetic, right? Because there are no electrons there, right? And so this question is just asking what has unpaired electrons. So we have to write the electron configurations. All right. And so I think if we go through these, all of these are 2+ cations. So nickel, 2+, cobalt, 2+, manganese, 2+. And I think if you use the periodic table and remove two of the valence electrons, we remove our s electrons first. Iron 2+ is D6, nickel is D8, cobalt is D7, and manganese is D5. And so what you'll see here is that manganese, because there's 5 d electrons, there's just 1 unpaired electron each one. I'm pretty sure the answer is D. If you draw the other ones, you'll see that iron actually only has 4 unpaired, nickel has 2 unpaired, this one has 4 unpaired, and then, 3, and then this one has 5. And so having 5 unpaired will make it respond the most to a magnetic field, making it paramagnetic. Versus something that is, you said permanent magnet, is a permanent magnet paramagnetic? No, it's ferromagnetic. So ferromagnetism means that when I have atoms of like iron 2+ next to one another, that their unpaired electrons affect one another. And so when you have a large like assembly of many iron atoms where all of the unpaired electrons are oriented the same way on different iron atoms, this is a ferromagnetic material. This is a permanent magnet, right? So there's a difference here. Not all paramagnetic materials are ferromagnetic. So just, I guess, would memorize that permanent magnets are ferromagnetic. Versus like diatomic oxygen is actually paramagnetic, all right, like liquid oxygen, and it responds to a magnetic field, but it's not a permanent magnet because there's so much energy embedded in those oxygen molecules that they're just bouncing around like idiots where their unpaired electrons aren't affecting one another. So there's no permanent magnetic moment, even because they're all spinning around randomly. But when you have an assembly of like solid particles like irons and they all orient their spins in the same direction, you do produce a permanent magnet. Okay, question, yeah.
Is this something like, I don't know, I think it came up once or twice the rest of the
Uh-huh.
Or like things like chromium and copper that are like one away from having half full.
Mm-hmm. Correct, yeah. So the reason here is, so the question was chromium and copper. So do you remember in 1210 that chromium and copper, when we did neutral electron configurations, those are our exceptions. That chromium, if you just went off the periodic table and you knew nothing about electrons and stability, you would think it is S2D4, but D shells, especially D shells, actually all shells, they get enhanced stability if you can half fill it. So right now that D shell is only 40% filled. So what is going to happen is one of those S electrons jump ship in a neutral chromium to make S1D5. So now we have 2 half-filled shells, and there's enhanced stability there. And so when you form a chromium cation, you always remove the S electrons first before you start doing inner D electrons. We see the same thing in silver, right? So silver, just like copper, you would think it's S2D9, but you have a D shell that's 90% filled. So what happens is one of those S electrons jump ship, and you see S1D10 instead. So you have a nice filled cup and like one just half filled cup in your S shell. And so looking at silver, which electron is most likely to be lost? That S electron. But once you remove that S electron to make silver plus, is it likely you'll remove additional D electrons? No. And so silver, does silver form any other cations? It just forms silver 1. And this is the reason, because of that anomalous neutral electron configuration. Do you have one of the periodic tables I gave you? You have one? Yeah, if you look on there, you actually see the neutral ones, and you'll see all of the exceptions. There's actually more exceptions, but we usually focus on just like chromium and copper and silver and stuff, but you actually see all of them in there. But in general, you always remove outer S electrons first before you do inner D electrons for making your cations. Good? Okay. Okay, let's blow up big K. Let's be done with it. Okay. They did give me a lighter this time, so yes. And then we'll be done. I don't know if you're happy or not. I'm real happy. I just have to get through 2 hours today. Yeah. Okay, so we'll blow this up. I hope you all enjoyed this class. Actually, I wanted to bring something up real quick. I always end class with this. This year, and especially with 1220, I like to dispel a lot of chemistry misconceptions. I feel like media, they always associate chemistry with like evil things. Even in that word cloud, a lot of students were like, wrote Walter White. When people think about chemistry, they think about Walter White. But the problem isn't Breaking Bad and Walter White. Oh, I'll point out, if you didn't sign your our class board, it's back there with Austin. If you want to sign it and leave a piece of yourself with me before you leave. I'll have it at the review session too. But the thing is yeah, they oftentimes associate chemists and scientists with like evil things. It sucks. It's like Snape before he had his redemption arc. He was considered the potions master. Even Plankton, he like was a scientist and was the evil guy. Walter White in Breaking Bad was a chemist and like super evil. I actually never watched Breaking Bad. Or even in like newer media, in Wonder Woman, like the antagonist was a chemist, and literally their name was Dr. Poison. Like, that's not even creative, right? And so my whole thing about I love chemistry so much, and I really hope to kind of dispel those misconceptions that are there out in the media, because I hate that chemists are always associated with evil things. But I did, using my brain, thought of one example of a chemist being good, and that is Honey Lemon from Big Hero 6. Yeah, she was good, right? And used her chemistry skills for good. And I'll point out that, like, I saw this thing, if you've ever seen the movie, when she, like, makes her bomb things, she, like, has a purse that literally has the periodic table in it. And so when she wants to, like, build her bomb, she, like, types in the formula to make it. And so, like normal people are, like, amazed by that. They're like, oh, she's, like, creating this out of nothing, right? Making the chemical formula. But we just learned in this class that it's not just composition that dictates chemical reactivity, it's also structure. So technically she could not make these bombs with those characteristics just from the composition alone. So do remember that. All right, so that's where I wanted to end it off with. So thank you, everyone. We'll end this class. Remember to do the ears thing, very, very loud. Don't want you to have tinnitus. Oh, you're gonna back up? Okay. So, yes, ears. Oh wait, I wanna make it darker. Ah, there we go. Okay. It's been a great year, everybody. Okay, good enough. All right. Oh yeah, the balloons say big K. Can you see it? Yeah, we're gonna be done with big K. All right, ears, everybody. Yay! Woo! Angie makes them so big. When it's their student workers, they make them a lot smaller. All right. Woo! Okay, last one. And then we're done with 1220. There we go. That one's different. Yes. All right. It's been a great year, everybody. See you at the review.